How does a satellite figure out exactly where you are on Earth? Today we'll answer that question step by step. Let's start with a single satellite. It knows its own exact position. It measures how long its signal takes to reach you. Multiplying the speed of light by this time gives us one distance. But a single distance from a known point doesn't give one location. It gives an entire circle of possibilities. Now we add a second satellite with its own distance measurement, giving us a second circle. The intersection of the two circles narrows the possibilities down from an entire circle to just 2 points. A third satellite adds a third circle. The intersection of all three circles pins down exactly 1 point, your true location. This simple geometric idea is called trilateration, and it's the core of how satellite positioning works. So why do real receivers need a fourth satellite, not just 3? Satellites carry atomic clocks, accurate to billionths of a second. But the clock inside your phone is a cheap quartz clock, and it drifts. A timing error of just 1 microsecond shifts your calculated position by about 300 meters, since that's how far light travels in that time. Every satellite gives us one equation. Your distance to it equals the square root of the square differences in x, y, and z, plus your receiver's clock error times the speed of light. Your position has 3 unknowns, x, y, and z, plus a fourth unknown, that clock error itself. 3 satellites give only 3 equations for 4 unknowns, so there's no unique solution, just a curve of possibilities. A fourth satellite adds a fourth equation. Now we have 4 equations and 4 unknowns, exactly enough to solve for 1 unique position, and cancel the clock error automatically in the process. So how accurate is all this? A typical receiver locates you horizontally within about 3 to 5 meters. But vertical accuracy is usually 2 to 3 times worse, often 10 to 15 meters, because satellites overhead form a wide, flat geometry, strong for horizontal position but weak for vertical position. To improve this, modern devices add a barometric pressure sensor. It measures the local air pressure around you and compares it to a known reference pressure for your area, since pressure drops in a very predictable way as you go up. This lets the device estimate your height far more precisely, even enough to guess which floor of a building you're on. In the next video, we'll explore the fascinating relationship between GPS and Einstein's theory of relativity, and how a difference of mere fractions of a second can shift your position by kilometers. See you in the next video.